Hello everyone. Firstly, I'd like to thank Department of Physics, our honorable teacher Dr. C.P. Khatiwada, Namchi Government College and Sikkim University for giving me this platform to make a presentation for the partial fulfillment of BSc Honors Physics 6th semester 2021. I am Praveen Pradhan, roll number 18 NS0002, and my topic for today's presentation is alkali metal spectra. Those elements which are present at the first period of periodic table except hydrogen are called alkali metals. As we can see from the electronic configuration of alkali metals, it consists of only one electron in its outermost shell, in addition to the completely filled subshells, which means that electron in s orbital from its valence shell will transist to form or to give spectra. Among all these alkali metals, we will make energy level diagram for sodium since it is easy to draw and understand the sodium spectra. To draw the energy label diagram of sodium, we will first make two lines. On the left, we will mark scale for energy in electron volt from 0 to -6. After that, we have to draw the energy level of hydrogen as a reference. I'm using red lines to show that hydrogen is for reference. So we know that energy level for hydrogen En will be equals to minus 13.6 by n square electron volt. Therefore, when n equals to 2, we will get minus 3.4 electron volt. Hence, we will draw a line for n equals to 2 from minus 3.4 electron volt like this. So another, for n equals to 3 we have minus 1.5, therefore we will draw a line from minus 1.5 for n equals to 3, and similarly for n equals to 4, n equals to 5 and n equals to 6 we will draw lines respectively. After completing the energy labels for hydrogen, we will see the orbitals of sodium. So since you can see from this, the transition occurs mainly from 3s orbital, therefore we start from making 3s orbital to its higher state orbitals. We need to remember this, that 3s orbital lies above -6, therefore we will draw 3s here. 4s lies below n equals to 3, 5s below 4, that is n equals to 4, 6s below 5, n equal to 5, and 7s below n equals to 6, but we don't need it, so we will not be drawing 7s. For p orbital lies above the energy level of hydrogen, that is 3p orbital lies above n equals to 2, 4p lies above n equals to 3, 5p lies above n equals to 4, and 6p above n equals to 5. For d orbital, it lies below, that means 3d orbital lies below n equals to 3, 4d below n equals to 4, 5d below n equals to 5, and 6d below n equals to 6. For f orbital, we know that the energy level for d orbital and f orbital are almost similar. Therefore, we will draw the orbital f orbital beside d orbital, that is 4f orbital beside 4d, 5f beside 5d, and 6f beside 6d. So these are the positions of the orbital for energy label diagram of sodium metal. After this, we have to understand how the electron can transist in the energy label diagram of sodium metal. So we have already studied in hydrogen spectrum that the electron could transist from nth label, from 1 2 3 4 5 to any label to ground state, giving different spectras. But in our case, there are certain criteria which needs to be fulfilled for the successive transition of electrons from its higher state to its lower energy state. There are three criteria in selection rule which needs to be followed for the successive transition of electron. That is, the first rule, the first criteria is delta L, that is the orbital quantum number, the difference between the orbital quantum number of two orbitals must be +1 or -1. Similarly, the second criteria is delta n should be an integer, that is the difference between principal quantum number between two orbitals must be an integer. It should not be negative or 0. Third criteria is delta J equals to 0 or +1 and -1. That is, the difference between total angular quantum number of two orbitals must be 0 or +-1. Using this selection rule, we can check the possibility for electron to transit from its higher state to its lower state. So we will check from ns to 3s, that is from 4s, 5s and 6s to 3s. The first criteria delta L, we know that for ns the orbital quantum number of s is 0, therefore 0 minus, again 3 from 3s its s orbital quantum number is also 0, that means 0 minus 0 equals to 0. So it does not follow the criteria, the first criteria of selection rule. Hence it's not possible for an electron to transit from ns, that may be from 4s, 5s or 6s to 3s orbital. Now from np to 3s, delta L equals to, we know that for np, for p orbital the orbital quantum number is 1, and for s orbital the orbital quantum number is 0, that means 1 minus 0 will be equals to 0. So it follows the first criteria of selection rule, so it is possible by saying that. Also we'll check from nd to 3s, we'll get delta L equals to 2, so it's also not possible. From nf to 3s, delta L will get 3, so it's also not possible. Now we can say that only from np to 3s the transition of electron is possible. Therefore we will draw a line from 3p, 4p, 5p and 6p to 3s respectively, and this series of spectra is called principal series. You have to remember that. And also now we will check for the transition of electron towards 3p. First we will check from ns to 3p. When we know that delta L, the orbital quantum number for s is 0 and orbital quantum number for p is 1, that means 0 minus 1 equals to -1. So it follows the first criteria, so it's possible for an electron to transit from s orbital to 3p orbital, from ns orbital to 3p orbital. Similarly from nd to 3p we'll get delta L equals to 1, so it's also possible. For nf to 3p we'll get delta L equals to 3. It's not possible because it does not follow the first criteria of selection rule. So from this we can say that the electron could transit from ns and nd to 3p. Therefore we will draw a line for ns to 3p, that is from 4s, 5s and 6s to 3p, and this series of line, this series of spectra is called sharp series. Also the second possibility we will draw from 3d, 4d, 5d and 6d to 3p, and this series of spectra is called diffuse series. Similarly, using selection rule, only the transition is possible from nf to 3d. Therefore we will draw a line from 4f, 5f and 6f to 3d respectively, and this series of spectra is called fundamental series. The equation or the wave number for all the series, that is principal, sharp, diffuse and fundamental series, can be written as Vp equals to R by 1 plus mu s whole square minus R by 1 plus mu p whole square for principal series. We can remember that the transition occurs from Np to 3s, therefore we have written mu p at the back and mu s at the front, that is 1 plus mu s at the front since it's towards 3s, and mu p at the back 1 plus mu p whole square at the back since it's from Np. Similarly, for sharp series, that will be Vs equals to, it's also from Ns to 3p, that means mu s is also written at the back and mu p at the front. And for diffuse series, we have Vs equals to R by 1 plus mu p since it's towards 3p, and minus R by 1 plus mu d whole square since mu d because it's from Nd, the electron is transiting from Nd. Similarly, for fundamental series, we can write the equation like this, where this mu s, mu p, mu d and mu f are called Rydberg corrections, since these equations are given by Rydberg for principal series, for principal, sharp, diffuse and fundamental series. Now principal series, since all the electron that is transiting from F to D and D to P and from 6s to 3p, all the electrons that is transiting from higher level must come to the ground state, that is 3s. So the only series, that is principal series, is the most bright and intense series among all the series, since all the electrons that is transiting must come to the 3s from this principal series. And also it's the only one that shows the absorption spectra and emission spectra, because as we can see from the first criteria of selection rule, only the electron could go from 3s to 3p and 4p or any np orbitals. Therefore it absorbs energy in 3s orbital only, hence the absorption spectra appears in this series, and also it shows emission spectra as well. But in all that three series we cannot see absorption spectra. For sharp series it is a fine lines, and we can see diffuse series as a broader lines, and for fundamental series always lies in infrared region. In this topic we have to remember the criteria which is to be followed for the successive transition of electrons to give us the spectra, and we also need to understand, we also need to know how to draw this energy level diagram of sodium metal. I hope you have understood this very topic, and thank you very much for watching.